So we're going through the development of the theory and practice of organic chemistry generation by generation. We started with Lavoisier, and then Berzelius and Gay-Lussac and Davy. And last time we did Dumas and Liebig and Buller. And now we're on to the next generation, people that were born around 1830. And the new developments are going to be valence and benzene. Remember, in this list, things that are in boldface are experimental, and things that are theoretical are in normal face. So valence and benzene is experimental, but what we're interested in is the theory of benzene here. And the people who are associated with this are Auguste Kekule, and you've all heard of Kekule structures and Kekule benzene, and he's memorialized on the front of the building here, born in 1829. But few of you probably have heard of Archibald Couper, who is not on the front of the building and was born 2 years later in 1831. This is Couper as a student. He lived to a reasonable age, 61 years old, but everything he did early. He was a sort of a dilettante student. He was a native of Scotland and studied in Edinburgh, but also went to Berlin often. And he studied classics and metaphysics, logic, moral philosophy, went to a lot of concerts. But while in Berlin, he got fascinated by chemistry. So in 1855, he became a student chemist. And in 1856, he went to Paris to work with Wurtz, who was the other leading French chemist, and worked indeed on salicylic acid, as you have done. In 1858, while in Wurtz's lab, he got fired for reasons that you'll see. And he went back to Scotland and tried to make a career there, but soon he had a mental breakdown, and the rest of his life he didn't do anything. Okay? But what he did in 1858 is really something. Okay? So he didn't get a stone on the front of our building. But on this building, which is to let, or at least was a few years ago, in Kirkintilloch, which is about 8 miles northeast of Glasgow in Scotland, there's a stone. And it says, this plaque marks the birthplace of Archibald Scott Couper, whose brilliant pioneering contributions to chemical theory have won for him international renown, and whose genius, stifled by an early illness, was denied the opportunity of consummation. When he was recovering from his first breakdown, he went fishing on this Endrick Water north of Glasgow and got sunstroke, which did him in for the rest of his life. And that's where he lived. His mother nursed him for his final 33 years in this house in Kirkintilloch. So this is the paper. He tried to publish it in French. He submitted it to his boss, Wurtz, in the hopes that he would put it in the French journal, but Wurtz thought it was not such a, was a little rash as a paper, and put it in his desk to cool off for a while. And in the meantime, Kekule published, which irritated Couper no little. And he told Wurtz what he thought about it, which was why he got sacked. But he also published it in English, and later it was published in French. But this is the English version, not the first version he wrote, by Archibald Scott Couper. And the first sentence already is fascinating. The end of chemistry, that is, the goal of chemistry, is its theory. Not many people would have said that. They would have had more practical motivations for chemistry. But Couper was a big thinker. He said, "The guide in chemical research is a theory. It is therefore of the greatest importance to ascertain whether the theories at present adopted by chemists are adequate to the explanation of chemical phenomena, or at least based upon the true principles which ought to regulate scientific research." So what were the theories that were prevalent at this time by 1850? Name one. Shai?
Dualism.
Dualism, okay, the radical theory. That was prevalent in Germany. How about elsewhere, like France? The substitution or type or unitary theory. Okay, so those were the big theories. Among those which have been lately developed, there is one on account of its apparent numerous merits, which particularly claims investigation, and respecting which we deem that it would not be unprofitable were either new proofs of its scientific value furnished, or, on the contrary, should considerations be adduced establishing not only its inadequacy to the explanation, but its ultimate detriment to the progress of science. I allude to the system of types as advocated by Gerhardt. So Gerhardt and Laurent, who were slightly second-level French chemists, were the ones who really came up with the idea of the type theory, but Dumas adopted and advocated it and was the leader. So anyhow, so this was the theory that was going on in the lab where he was present in Paris. So, page 106 of this paper on the French type theory, he said, should the principle which is therein adopted be applied to common events of life, it will be found that it is simply absurd. Suppose that someone were to systematize the formation of letters into words that form the contents of a book. Were he to begin by saying that he had discovered a certain word, which would serve as a type. Remember, there were 4 types, right? Water, ammonia, HCl, and hydrogen. And from which, by substitution and double decomposition, all the others are to be derived. That he by this means not only could form new words, but new books. And books almost ad infinitum. He would state certainly an empirical truth. That is, you can take some word, substitute letters or pairs of letters or sets of letters for other letters and get any word you want. Okay? At the same time, however, this method would, judged by the light of common sense, be an absurdity. But a principle which common sense brands with absurdity is philosophically false and a scientific blunder. So this was not likely to make him popular in Paris. At the same time, however, here's what he was doing, actually, right? The emperor's new clothes. He's a new guy on the block, right? He's only been a chemist for 2 years, only begun studying chemistry 2 years before, and says what everybody's doing is nonsense in France. Well, how about in Germany? That's where he was before, in Berlin. I can only remark that it is not merely an unprofitable figure of language, but is injurious to science, inasmuch as it tends to arrest scientific inquiry by adopting the notion that these quasi-elements, what does he mean by the quasi-elements? What are they? Compound radicals, right? Contain some unknown and ultimate power which it is impossible to explain. That is, okay, so you got radicals. What holds the radicals together? Right? It stifles inquiry at the very point where an explanation is demanded by putting the seal of elements, of ultimate powers, on bodies which are known to be anything but this. They're definitely not elements, because you can burn them, of course, and get water and CO2 and so on. Okay? So this was absolutely true on both counts, both the French and the German theory, but it was stated pretty undiplomatically, right? And especially for someone who'd only been studying chemistry for 2 years. Maybe it took someone who was only studying chemistry 2 years to see how stupid it was, right? But at any rate, he got in trouble because of this. What did he offer as an alternative? To look at the properties of the elements themselves, not of radicals, not of these planetary systems that were the types. Science demands the strict adherence to a principle in direct contradiction to this view. That first principle without which research cannot advance a step dare not be ignored, namely, that a whole is simply the derivative of its parts. So if you have to understand the elements, and then you can understand assemblies of elements from that. That's not obviously true. In fact, I think you could make a pretty good argument that as you get things more complicated, they're not simply a sum of their parts. But that's what he said. As a consequence of this, it follows that it is absolutely necessary to scientific unity and research to consider these bodies as entirely derivative and as containing no secret ultimate power whatever, and that the properties which these so-called quasi-elements possess are a direct consequence of the properties of the individual elements of which they are made up. So study the elements, not the radicals. And he began by saying he'll focus on carbon, which is not surprising for an organic chemist. In applying this method, I propose at present to consider the single element carbon. This body is found to have 2 highly distinguishing characteristics. One, it combines with equal numbers of hydrogen, chlorine, oxygen, sulfur, etc. Would you agree with that? How could he say so? It's because he wasn't dealing with the right atomic weights, right? Okay. It enters into chemical union with itself. So those are the two things, that it'll unite with itself, not just with other things, the way dualism would like you to do. And it combines with, it has a certain combining power. These two properties, in my opinion, explain all that is characteristic of organic chemistry. So 1858 marks a new frontier in organic chemistry, a completely new revelation. The tetravalence and self-linking of carbon, that's points 1 and 2, right? That it combines with a certain number of other things and it can link to itself, right? Now, here he shows the formula of methane, of CO2, and of carbon tetrachloride. But those are the atomic weights he's using in order to get these formulas. Notice he says, here the whole 4 of hydrogen are not bound by a mutual affinity. You know that they're not all collected together because you can substitute them one by one, 1 chlorine, 2 chlorines, 3 chlorines. For each element of hydrogen can be substituted for one of chlorine in a regular series, beginning with the first, ending with the last. The atoms of oxygen are, on the contrary, united in pairs. What does he mean by that? That the oxygens are united in pairs. Why are they united in pairs in his formulas? Drawn by those curly brackets like they had in type theory. Yeah, Angela?
Probably one oxygen because they were probably one oxygen because his weight is half of.
Aha, because he had half the atomic weight, so they always came in pairs, right, to get oxygen 16 if he thinks oxygen is 8. The atoms of oxygen are in pairs, which will be more fully developed hereafter. Not in this paper, but there was no hereafter because of his breakdown, okay? And only for 2 atoms of oxygen, 2 chlorines can be substituted thus. So you can start with CO2, get phosgene and carbon tetrachloride. In the same manner with bodies that contain multiples of C2 united to hydrogen. So carbon is the same deal. It always comes in pairs, right? Because its atomic weight is 6 instead of 12. Okay. Take the inverse of this. If the 4 atoms of hydrogen were bound together, we could evidently expect to form such bodies as H4Cl4, right? If the 4 were all held together and could make 4 bonds, right, then you could get H4Cl4 or these other compounds. One would naturally expect to find carbon substituted for chlorine, find bodies like H4Cl2, C2, and so on. These bodies are not only unknown, but the whole history of hydrogen might be investigated and not a single instance be found in favor of the opinion that it has any affinity for itself when in union with another element. Okay? So that, remember, getting all the chlorines together was Schindler's idea. Okay, so here, now that he have the idea that these atoms associate together, it makes sense to talk about a structure, right? What's connected to what's connected to what, you know, the toe bone and the ankle bone and all that stuff. Okay, so now you could write structural formulas. So these were the very first structural formulae, because before this there was no such thing as structure. Okay? Thus methylic alcohol has this formula and ethylic alcohol has the other. So now do you see the theme here? What's he using to denote bonds? 3 dots, right, are a bond. So he has a carbon bonded to 3 H's and also to OH. That's because oxygen is doubled, right? So we would write it this way. Or ethyl alcohol, we would write that way. Okay? Or this compound. Now, this one has a printer's error in it. What is it? And what's the printer's error? What's the substance? Seth, can you read it off to me? Start from the left, bottom left. What is it? What's the first group? There's a carbon. That's a single carbon, right? Yeah, methyl, CH3, right? He doesn't draw the 3 bonds to hydrogen separately, but it's clearly being C bonded to 3 hydrogens. What's next? Keep going. It's a C bonded to what? The top left. It's bonded to the methyl, of course. What else? It's bonded to oxygen, to a single oxygen, although we wrote 2, right? And what else is that carbon bonded to?
Hydrogen.
How many? How many hydrogens is it bonded to? The top left carbon. To 2. So it's CH3, CH2O. Now, can someone help me out with the rest of it? Ryan?
Well, wouldn't that only just be one O at the top? Because
It should be 1O, but he's got the different atomic weight. John?
Shouldn't the C's on the far right be
Ah, the C's on the far right should be bonded to one another. The printer left that out. So it's symmetrical. It's diethyl ether. Okay, and it's the correct structure for it, except for the printer's error. Okay? Now, he says, there is no reaction found where it is known that C2 is divided into 2 parts. It is only consequent, therefore, to write, as Gerhardt does, C2 simply as C, it being understood that the equivalent of carbon is 12. So he changed it in this paper to be 12. So now his formulas are going to be more like ours, right, without the C2. So he has a formula for glycerin and one for glyceric acid. So let's do glyceric acid. What do you see up at the top? What's the top carbon? Max, what do you say? What's it bonded to, the carbon at the top on the right?
Onto a hydrogen,
1 hydrogen,
OH group,
an OH group,
and another
pardon me?
another OH group,
2 OH groups,
and then
and the carbon below, right? Because carbon can bond to carbon. That's the special thing about it. Okay, so here's the one on the left in a formula nowadays, and there's the one on the right. And it turns out he guessed a bit wrong, because he put 2 OHs on the top carbon and none on the middle one, and it should be the other way around. So in truth, he should have changed those 2. Of course, he had no way of knowing it. And the same on the right. Okay, so but he's pretty close with his structure. But probably the most remarkable thing is his structure for glucose, which is shown here, and which, now he doesn't show the vertical bonds between carbons. He uses this curly bracket, so that's a little reminiscent of type theory. But clearly that's what he meant, was the carbons to be bonded to carbons. So that's the formula he wrote. And that's the correct structure for glucose if it's hydrated. Okay? So you can add, glucose is an aldehyde, CHO on the bottom, double bond O. So you can add water to the aldehyde, that actually happens, and you get the structure he wrote here. So it's right if the glucose is in water, right? So try yourself. This is a good exercise for reviewing what we've been doing. Try, it's depending on how you define it, it's a 2 or a 3-step sequence of homo-lumo interactions that take water plus an aldehyde into a diol, which is what you have here. So try that one out. Okay. And in the French version of the same paper, which as we said appeared a little later, he drew it this way. And what do you notice is different now? There's 2 things different, actually. Yeah, now he's drawing single lines, straight lines for bonds. So this is the first time that was done, none of these dotted lines anymore. But there's a typo. Instead of drawing OH here, and notice, instead of drawing OOH here for a second, he's got the wrong formula. It's got H2 there. But this is really amazing that he got the correct structure for such a complicated molecule in the very first paper where the idea of structure or of bonds altogether was proposed. So this is really amazing. And we owe to Couper the idea of bonds and the notation we used to do them. So here's Old Isle Cemetery in Kirkintilloch in Scotland yesterday. And there you see that this is the gravestone of Archibald Scott Couper. And down here is your thank you note. And those are the flowers. That's the heather you bought to put on his tombstone. So that was our secret thank you note. And we thank Susan Frew for being our agent and delivering this yesterday. Okay. But on the front of the building, Couper doesn't get any notice at all. It's only you guys that are in the know that can do that, right? On the front of the building, they say Kekule. So let's talk about Kekule. And we'll also talk about Hoffmann, whom we mentioned before as the guy in the top hat on the right end of that picture in Liebig's lab in Gießen. And Canizzaro. Okay, this is a drawing that Kekule made at the age of 13. By my standards, that's a pretty darn good drawing. And here's one he made at the age of 18. And he went to Gießen University to study architecture, right? But while he was there, he went to Liebig's lectures and got fascinated by chemistry and became a chemist. Okay, he studied with Liebig, and after he finished, he wanted to go to Paris to study with the people there. What do you think? Liebig, remember, had worked with Gay-Lussac, so he knew from Paris. What do you think he would tell Liebig, the young guy about to go off to Paris?
Stay away from Dumas.
Stay away from Dumas, perhaps, right? What he said was, there you will broaden your horizons. There you will learn a new language. There you will learn to know the life of a great city. But there you will not learn chemistry. But he went anyhow. He also went to England and became widely acquainted with all the leading chemists of the day. Then he got a job in Heidelberg, where he was from 1856 to 58, and he did research on cacodyl, that's that free radical involving arsenic. A remarkable thing, his student who worked with him on that was Bayer, whom we'll talk about a lot later. That was Bunsen, who was the big cheese in Heidelberg, was the one Kekule was associated with. And he did the work not in a laboratory, but in the kitchen in his apartment, this work on arsenic. So in 1857, while he was there, he proposed a new type, right, based on carbon. So carbon could have 4 things attached to it, which you could substitute one for another, right? So this was where he got the idea of carbon being something special, the basis of a new type, and that it was tetravalent. And ultimately, he got onto the idea a year later that carbon could link to itself. So he had proposed the marsh gas type before Cooper's paper, but this other one was essentially simultaneous, just slightly later written, but earlier published. Here are his observations on Mr. Cooper's new chemical theory. In fact, in 2 memoirs which have appeared in Liebig's Annalen, I've put forward different views which, in my opinion, should furnish a clearer insight into the constitution of chemical compounds, clearer than Cooper's. I may be allowed to indicate that my first paper lays down the principle which I have called the basicity of atoms. We'd say valence. If Mr. Couper thinks he has discovered the cause of this difference of basicity and the existence of a special kind of affinity, I am the first to admit that I have no right to contest his priority in this. But he was quick to say that he was the one that had the idea first. And he went on to quite a successful career in contrast to Couper. Here he is in Ghent, the period during which he proposed the structure for benzene with a bunch of people whom we will talk about later, or at least several of them we'll talk about later as his students. And then he became the leader in Bonn in a big new chemistry institute there. Here he is in 1872, and we'll talk a lot about this guy on the right here. So he became a really prime leader in chemistry. Now, facts, ideas, and words. Words means nomenclature. So these new ideas needed new words. And also, not just the words written out with letters, but notation. What symbols are you going to write for these things? And a further development of that is actual physical models that you could put together, right, to show what you're talking about with molecules if they have structure. So Hoffmann was great with language. He actually went and became a leading professor in the Royal College of Chemistry in London, because Prince Albert, Victorian Albert was a German. So he had a lot of connections with German chemistry and went to Liebig. Liebig said, Hoffmann's a great guy, you should get him. So they got him. So he came to London and was completely fluent in English and very good at languages altogether. And he had the idea of systematizing the names of hydrocarbons. He was going to base it on Latin roots. So 4 will be quart. Right? What do we say for 4? butane, right? We talked about that last time. So quartane is the start. And then you can start pulling hydrogens off and have names for the radicals. So if you pull one hydrogen off, it's quartile, because eel, remember, is the root that means radical. And then you can pull a second hydrogen off, then you have quartene. And then you pull a third hydrogen off, it's quartene-eel. And then quartine, quartine-eel, quartone, quartone-eel, quartune, quartone-eel. What was this system? How can you remember which one is quartune? Yeah. It's the vowels in order, A, E, I, O, U. And we preserve the A, the E, and the I, although we write Y instead of I for alkyne, right? That's where it came from Hoffman. But the quart didn't stick because bute was well established by then. Okay, now how about Kekulé's, so that's words, how about notation? So in the paper where he proposed benzene in 1865 while he was in Ghent, he says, in a footnote, for greater clarity, I am presenting at the end of this note a table giving graphical formulae for most of the substances mentioned. The idea that these formulae are designed to express is rather well known now, so it will not be necessary to dwell upon it. I'm keeping the form that I adopted in 1859 when expressing for the first time my views on the atomic constitution of molecules. So 1859 was at the time he was proposing valence, and so on 1858 was that, remember? So this is now 5, 6 years later, and he's applying it to benzene. This form is nearly identical with that which Monsieur Wurtz used in his beautiful lectures on chemical philosophy. It seems to me preferable to the modifications proposed by Messrs. Loschmidt and Crum-Brown. So let's first look at what Loschmidt did in Crum-Brown. So here's what they said, to which Kekule considers his superior. Well, first let's think, what should a formula show, right? What's the very first thing a formula should show? It has to correspond with the facts, right? So what facts do you deduce about a molecule? What should a formula show? Kevin?
What elements are in the...
What elements are there? Carbon, hydrogen, oxygen, chlorine, nitrogen, whatever. Okay, what else? Shai?
The ratio of those elements.
The ratio of the elements, right? The Berzelius also had this. But what's going to be new? I think I've got that there, right? Composition, the elements and the number of atoms. What next? Now you got the new theory, the valence theory. Sherwin?
Structure.
The structure, what do you mean by the structure?
The relative positioning?
You mean like X, Y, Z coordinates? You could write, numbers. Here's the origin. I'm going to give this, 1.238 and so on. What?
Then which atoms are formed?
Which ones are connected to one another, right? Not their positions in space, but this is connected to this valence goes there, and so on. Okay, so Berzelius was already fine for composition, but now we also need to show constitution. That's the second C, is constitution, which means the nature and sequence of bonds. Now, sequence is clear. This is bonded to this, bonded to this. What do I mean by the nature of the bond? How could bonds differ in their nature? Single, double, triple, right? Okay. So, and you need to be able to show isomers, which Berzelius couldn't show. Okay, so here's Loschmidt. This is Loschmidt's formula, 1861, for acetic acid. Can you understand it? Andrew, what do you say? No hope? What do you think the stuff on the left is? Pardon me? CH3, right? So the size is something about the weight, right? So it's CH3, what's it bonded to? C, same size. What's it bonded to? O, H, and what's special? Double bond. So he's got a way of showing a double bond, right? So we can easily understand it. Okay, now here's Crum-Brown. Now that's benzoic acid in Crum-Brown's paper. So the COOH is even clearer than it was in Loschmidt, right? What's a double and single bond? The same thing we use now, okay? What's different is the C6 part and 5 hydrogens attached to it, but we don't really know how the C6 is arranged, although he also showed this one for phenol, which is a benzene with a hydroxyl group on it, OH. So there you see a ring, double, single, double, single, double, single, And H is attached to all the carbons except for one, which has OH. So that's easy to understand. Shai?
Where does the idea of double bonds come from? I feel like it's just.
Because if you say carbon has 4, then you have to figure out where the 4th one is, right? If it's associated with 3 atoms but can make 4 bonds, it must make 2 to one of them. That's the idea anyhow. Or it could be, that they all go to the center of the ring, the 4th one, and so on. There are other ideas too. Okay, or here is a reaction in Crum-Brown's notation. So it's an aldehyde. You add a HOMO of cyanide and a proton to the O, and you get that compound, a cyanohydrin as it's called. So this is it's almost identical. What difference is it from our current? How different is it? We don't draw circles around the elements anymore. That makes it faster to draw. Otherwise, it's essentially the same. Okay? Or here, he says there are 2 kinds of alcohols. True alcohol, which can lose water and give an olefin, or olefin hydrate, which can lose water and give the same olefin. What's the difference between the true alcohol and the olefin hydrate? How are they isomers?
OH groups are the same.
Russell? Right, the position of the OH relative to the R. Right? So he's explaining isomers here too. So those are pretty good, but Kekule says his is ever so much better. This is Kekule's structure of benzene from that same paper. Remember, he says at the end, I'm going to give my superior formula. So what in the heck is he talking about? Eric, you got any idea? So what do you think that is? Eric? No idea? Well, you don't have much to work with in benzene. What do you have? It's C6H6, right? So that's got to either be carbon or hydrogen. Which do you think? The top left there. No idea? Anybody got an idea? Why do you say carbon, Kate?
Yeah, it's also showing double and single bonds.
It's showing up above here in the schematic one. It's showing double bonds between carbon and then a single bond, then a double bond, then a single bond, then a double bond. And, well, let's go. That's open chain, and this is closed chain. What are these arrows on the end? Those are the ones that loop back and attach to one another somehow to make a ring. Okay. Do you think he's trying to imply Cartesian coordinates for the location of every atom by where he draws these symbols? Right? He's trying to show X, Y, Z coordinates. What do you think, Nate? Think he thinks he's showing that or not? Either of you.
He's got X, Y, or he's got like X, Y.
I mean, you could say, right, here's an x-axis, here's a y-axis. This has certain coordinates, that.
Yeah.
Do you think he thinks that if he had a microscope and could see it, that's where those atoms would be, in fact? Is it physical position he's showing?
They look kind of like cells.
Kelsey, you got an idea? Do you think he thinks he's showing where these atoms are actually located in space? What is he showing? Yeah, Sherwin?
The sequence.
What's bonded to what, and whether it's single bond or double bond. He's showing constitution, the nature and sequence of bonds, not positions of atoms, certainly not. Okay, and then the little ones are hydrogens, right? So you got so the length of one of these things is how many valences it has, right? 4 long for carbon, only 1 long for hydrogen. And tangency then means a bond, right? So this is CH double bond, CH single bond, CH double bond, and so on. And then you get to the end, you go back to the beginning. Okay? Now, he then shows chlorinated benzene, because chlorine is also monovalent, right? So you can substitute it for hydrogen. And then you can have dichlorobenzene too, or tri or tetra, or so on, right? Now, is he showing isomers here? That is, in this case, if you substituted this one for chlorine instead of that one, same thing or different things? If you believed if you believed that this was a picture of things in space, they'd be different, right? But if all you're interested in is what's connected to what by single and double bonds, then it's the same. You have the same pattern either way. How about for the dichloro? Would there be isomers of that? You could get different sequence, right? They could be adjacent carbons that have chlorines, or next adjacent, or beyond that, right? So you could use this system to talk about isomers. So how many isomers? What do you think Kekule thought? What do you think he thought about how many isomers of chlorobenzene there are? Do you think he thought there were many? Just what? Yes. I'm going to show you. Okay, he thinks his system is superior. Now, he also used his system in this same paper. He did a lot of formulas, but he showed these compounds like this one. What's that group on the left? What's the group here? What is that? What's this atom? CH3. What's this? CH2. OH. O is 2 units long, right? So CH3, CH2, CH2, OH, alkyl propylic, propyl alcohol, okay? Now what's this one? CH3, CH3, CH, OH. It's alkyl methyl ethylic, methyl ethylic alcohol. So this would be ethyl alcohol, the part on the top, but we've got a methyl substituted in it. And notice he's having to change his formula, right? Because now these are horizontal tangencies that are bonds, but this vertical tangency doesn't count as a bond. So it's getting a little complicated to explain to students, right? Okay, what's the next one? CH3? What's this? C double bond O. CH3. So that's our old friend acetone. And what's this one? CH3, CHOH, right? CH3. Alkyl acetonique. So it's the alcohol you get by adding 2 hydrogens to acetone. Now, what do you think about this? Do you see anything interesting? This one is CH3, CHOH, CH3. This one is CH3, CH, CH3, OH. Sophie, what do you say?
They're the same thing.
They're the same nature and sequence of bonds, right? That one's what we know. That's that one, that one, that one. But the last and number 28 here are the same thing, but he draws different formulas for them. So his system is not showing isomerism properly, right? He drew these different. He didn't say they were the same, right? And they were thought to be different because when you prepare it one way and when you prepare it another way, you get a different boiling point, say, or something. I actually don't know what the data was, but there was some difference. It said there were these 2 different compounds. Did you ever get a wrong boiling point? So did they, right? It just turned out the experiment was wrong. But that shows that his system is not as good as these other systems, whatever he said. Okay, now how about physical models of molecules? Well, here's a great patent that was issued by the US Patent Office to Samuel M. Games of Glasgow, Kentucky in 1868. And we can read about his description of what's so good about this. He says, now, if a class thus instructed be at the recitation bench, so here's our recitation bench, right? And one of them is requested to form carbonic acid, he will walk quickly to the table in front where the box is open and place on one of the shelves a cube marked 6 and 2 marked 8. Carbon 1, oxygen 2. If requested to form lime, he will place on the shelf a cube marked 20 and another marked 8, oxygen, these being the elements of lime. These cubes being all placed in contact and the pupil being asked, what have we now? Answers, carbonate of lime. Right? Okay. Another pupil may then be asked to give the proximate analysis. for carbonate of lime. And the cubes before him will indicate the answer and fix it in his memory. It is composed of one equivalent of carbonic acid, 22, and one of lime, 28. You just pull them apart and you see what the proximate analysis is. Another may be requested to give the ultimate analysis. And by the same means, he is furnished with the answer. Carbonic acid is composed of one atom of carbon, 2 of oxygen, and lime is composed of one atom of calcium and 1 of oxygen. The intelligent educator will see at a glance that in this chemical alphabet, he has the means of at once arresting the attention of his class and converting what had hitherto been an irksome task into a pleasant recreation. The atomic theory, the characteristics of affinity, the law of multiple proportions, the nomenclature, isomerism, etc., may all be learned in half the time required heretofore and learned so as not likely ever to be forgotten. Now, what do you think? Would this show the atomic theory that molecules or substances are composed of atoms? Does it show it? Yeah. Okay, how about the characteristics of affinity? Single, double, triple bond, valence, and so on. Show that? Not in any obvious way that I can see. So I doubt that one. How about the law of multiple proportions? Remember what the law of multiple proportions was? You have the same elements. If you have A parts of A, B parts of B, and so on, all that stuff, then what AD will be and so on. Yeah, Max?
Why did Kekule only show 1 oxygen in his notation?
Pardon me?
Did Kekule know what the exact mass of oxygen was? Because he only had 1 in his notation.
Yeah, but notice everything here is halved,
Oh, okay.
so it's okay. They're right proportions, right? Okay. But multiple proportions, you have to know something about how many of one associates with how many of another, which isn't obvious here. Okay. Nomenclature? Well, maybe. Calcium oxide and so on, CO2. Isomerism, that you can have the same things differently arranged. Well, obviously you could put the blocks on top of one another or beside one another, but how do you know how many you should do, right? Not very clear to me that this system works well. So those models are good for some things, but not good for an awful lot of things. Okay, now James Dewar in Scotland, a student, had the idea of using brass strips to show models. And in fact, he could put these black balls on. He said, to make a combination look like an atom, a thin round disc of blackened brass can be placed under the central nut. I think that's really cute, to look like an atom, as if he knew what an atom looked like, right? Okay, so then he made these models from his strips of possible structures of benzene. Right? You can see where the atoms are and the 4 valences on every carbon and which direction they go. That particular one, that compound, that structure was actually prepared about 100 years later, and when it was called Dewar benzene. Right? That one's interesting. It's got a 4-center bond, 4 carbons all sharing the same bond, right? Hoffmann, the guy, remember, who was good at language and was in London, his last lecture in London was at the Royal Institution, the place where Faraday was and where Davy had been and did the experiments in electrolysis. So he gave this public lecture where he used croquet-balls for atom models with sticks stuck in them, and he colored them. And the system he chose is the one we still use for what color the atoms are. White for hydrogen, red for oxygen, blue for nitrogen, black for carbon. Okay, so here's part of the lecture he gave. So he would build molecules before your very eyes. He'd start with a hydrogen, put an oxygen on and another hydrogen. Lo, he's made water, right? Or he could make marsh gas, methane. Or he could show the oxides of HCl. So you start with HCl, but he could take it apart and put an oxygen in between, or put 2 oxygens, or 3 or 4 oxygens in between to go from hydrochloric to hypochlorous to chlorous to chloric to perchloric. So this is like Lavoisier, right? Going to different levels of oxidation. Unfortunately, those aren't the structures, right? What really happens is that the unshared pair of chlorine can share with oxygen to give this, which is the active ingredient in Clorox bleach. Or you can use another unshared pair of chlorine to put another oxygen. or another for another and get the oxidizing agent that Gay-Lussac used, the chlorate. Or you can put a last one, and this is an explosive. In fact, ammonium perchlorate, AP, is a component of military explosives. Notice that in Hoffman's thing, you could have put 15 oxygens in a row if you could have reached high enough, but you can only go to 4 here because that's how many unshared pairs chloride has to use. Okay, but then he showed the chlorination of marsh gas, so monochlorinated, dichlorinated, trichlorinated, and tetrachlorinated marsh gas. Now this is interesting because for the dichloro, you could imagine having 2 isomers with these models, right? The chlorines could be near one another or opposite one another, right? Now, some years later, there was an exhibition in London, and they showed molecular models. By this time, Hoffman was back in Germany, but they got a guy in Spain to make some Hoffman-style models. Manuel Gonzalez Rodriguez from Madrid made this set. And here's chloromethane made from that set. What's the difference between these? It says, according to Hoffman here, Segun A.W. Hoffman, right? What's the difference? Andrew? Or, yeah, what's it, Alex?
The bonds on the carbon aren't 90 degrees from each other.
They're not 90 degrees from one another. They're 109.5 degrees from one another. It's a tetrahedron, not a square plane. Right? Now, what does that say about isomers? So suppose we substitute another chlorine. There's a dichloro. There's a different dichloro. There's a different dichloro. How about it? They're just rotated from one another. They're not different. Right? So depending on whether it's square planar or tetrahedral, you'll get different numbers of isomers. That's neat because it gives you a tool for telling whether it's square planar or tetrahedral. Right? So you can get structure from analysis. So, but these constitutional models try to show the nature and sequence of bonds for Hoffman, not the arrangement in space, and not for Hoffman, and not for the guy that made these models. They weren't trying to explain isomers in that way. All they were trying to show was the same thing you draw in these pictures, the nature and the sequence of bonds, whether they're single or double, triple, and what's associated with what. So that comes a little later, trying to get to the arrangement in space. But the pièce de résistance of Hoffman's lecture was this, that if you take these croquet-ball models and make the olefiant gas, which we talked about last time, it's got 2 spare valences, and if you add chlorine, you can get the Dutch liquid, the dichloroethane. But remember what we saw last time. He called olefiant gas an unfinished or not saturated. We now call it unsaturated molecule. And it's reactive because of these dangling valences. And we now know why it's that way, that he's got the wrong structure, right? It should be CH2, not CH3. And we know about HOMOs and LUMOs now. But that was what he really showed, was that the model had something completely new that no one anticipated. It could explain what? That's new. What new quality is he associating with the models? What elements are there? What ratio they're in? Right? How they're linked to one another, single, double, triple bonds. What's he adding? Reactivity, right? So it's something new. So the whole history is adding new things, new properties to the models, and there are more to come, okay? That's it.